Hello, this is section 8.2, Simplifying Expressions with Radicals. Part 1, Product and Quotient Properties for Radicals. Product property of radicals. If the nth root of a and the nth root of b are real numbers and n is greater than or equal to 2 as an integer, then the nth root of a times b is just equal to the nth root of a times the nth root of b. Quotient property of radicals. If the nth root of a and the nth root of b are real numbers and b is not equal to 0, and n is greater than or equal to 2 is an integer, then the nth root of a divided by b is the nth root of a divided by the nth root of b. We can use these properties to help us simplify more complex expressions involving radicals. Note that a radical expression, the nth root of a, is considered simplify if it has no factors of m to the nth remaining in the radicand. Example 1. Simplify the expression the square root of 98. Now, the reason why this example is different than the previous section is there is actually no integer number multiplied by itself that equals 98. So step 1 is to find the largest factor in the radicand that is a perfect power of the index. Prime factorization can be helpful in identifying this factor. So I'm going prime factorize 98. Well, 98 is even, so I know 2 goes into it. 49 times 2 is a prime number, and 49 splits up into 7 and 7, which are also prime numbers. What this tree tells me is that 98 is equal to 2 times 7 squared. Step 2. Now I'm going to rewrite it like that, so the square root of 98 is equal to the square root of 2 times 7 squared. And then using the product property, this is the same thing as the square root of 2 times the square root of 7 squared. The square root of 7 squared will be the absolute value of 7, but the absolute value of 7 is just 7. And then we can't simplify the square root of 2 any further, so it'll be square root of 2. So the square root of 98 is equal to 7 times the square root of 2. Example 2, simplify the following expressions. Square root of 288. So again, I'm going to go 288 and break it up. Well, since it ends in 88, I know 4 goes into it, and it'll be 72 times. 4 is 2 and 2. 72 is 9 and 8. 9 is 3 and 3. 8 is 2 and 4. And then 4 is 2 and 2. So then I get the square root of 288 is equal to the square root of, I got 2 to the 5th power. But because I'm doing square roots, I want to collect things in square roots. So this would be 2 squared, because there's 2 of them, times 2 squared, so there's 4, and I'm left with 1, so I just get 2 to the 1st. And then we also have the 3 squared. This then becomes the square root of 2 squared times the square root of 2 squared times the square root of 2 times the square root of 3 squared, which is 2 times 2 times the square root of 2 times 3, and then 2 times 2 is 4 times 3 is 12 times the square root of 2. Now I did do this broken up the most simplified way, but we could have rewritten it as 12 times 12 times 2 and got the same answer. Okay. Cube root of 81. So this time, because the index is a 3, we want to group them in groups of 3, not 2. So 81 is 9 and 9, and then 9 is 3 and 3. So 81 has 4 3's in it. But again, I want groups of 3, so this would be 3 cubed times 3, which is the cubed root of 3 times the cubed root of, the cubed root of 3 cubed times the cubed root of 3, which is 3 cubed root of 3. So there are a lot of 3's in that answer. The fourth root of 729. So again, I'm going to take 729, break it up. We get 3 and 243. That becomes 3 and 81. Then 81, we already did on the previous page. So to do a little shortcut, I just know it breaks into 4 threes. But you could do the 2 nines, then the 4 threes. That's okay. I'm just trying to save a little time here. So then this becomes the fourth root of 729 is equal to the fourth root of 1, 2, 3, 4. So 3 to the fourth. But then we have 2 left over. So then this becomes the fourth root of 3 to the fourth times the fourth root of 3 squared, which becomes 3 times. Now I can't actually simplify the fourth root of 3 squared. That's just going to stay that way. So then that becomes the fourth root of 9, because 3 squared is 9. So that's how we do it with numbers. Now, the next example, the square root of b to the fifth, well, this is already in factored form. So I know b to the fifth is b squared times b squared times b to the first. So then I'm taking the square root of that, which is then the square root of b squared times the square root of b squared times the square root of b, which is the absolute value of b times the absolute value of b times the square root of b, which is the absolute value of b squared times the square root of b. Now here, the absolute values aren't needed because we're squaring it. So this is always going to be positive. So my open math would actually consider this not simplified all the way. You would need to rewrite it as b squared times the square root of b. On a test, I'm not going to be that picky though. Square root of 32y to the fifth. Now this, I'm going to use the product property right away to rewrite as the square root of 32 times the square root of y to the fifth. So that way I can do them separately. Now 32, I need to do a factor tree. What is that? 4 and 8, 2 and 2, 2 and 4, 2, 2. So then that becomes the square root of 2 squared times 2 squared times 2 times, and then y to the fifth. Well, the only thing that changed is I changed the b to a y. So I'm actually going to go straight to here, where this becomes y squared square root of y. And then this is the square root of 2 squared times the square root of 2 squared times the square root of 2 times y squared square root of y, which is 2 times 2 square root of 2 times y squared square root of y, which is 4 square root of 2 times y squared square root of y, which I then can combine the square roots and we get 4y squared square root of 2y. And there's our answer. Oh, the next one is the cubed root of 128 n to the 11th power. That should be 11th power. Okay. So again, I'm not going to write it out, but we are going to treat them separately. So 128, which is 2 and 64, which is 8 and 8, which is 3 twos. So then this becomes the cubed root of, and because it's cubed, I'm going to group them in threes. So we get 1, 2, 3, so 2 cubed. 1, 2, 3, 2 cubed. And then 1. N to the 11th, well, that again, groups of 3 would be n cubed, 6, 9, and then 11. Now I am going to start simplifying the writing. I'm not actually going to write cubed root of 2 cubed over and over again. It's just the cubed root of 2 cubed is 2. Cubed root of 2 cubed is 2. Cubed root of 2 cannot simplify. Cubed root of n cubed is n. Cubed root of n cubed is n. cubed root of n cubed is n, and then cubed root of n squared cannot simplify. So we get 4n cubed times the cubed root of 2n squared. Okay, square root of 45 over 80. When doing fractions, I do recommend like reducing first. So like we can reduce by 5. So this becomes the square root of 9 over 16, which then just becomes 3/4. Or the next one, the square root of m to the 6 over m to the 4th. Well, m to the 6 over m to the 4th is m squared. Square root of m squared, absolute value of m. Here we can reduce by 3, I'm pretty sure. Nope, can't reduce by 3. So this just becomes the square root of 27 times the square root of m cubed over the square root of 196. Now 196 is a perfect square already, so that's going to equal 14. Square root of 196 is 14. So now the 27 is 3 and 9, which is 3 and 3. So the square root of 27 is equal to the square root of 3 squared times 3, which is 3 times the square root of 3. And then the square root of m cubed is the square root of m squared times m, which is the absolute value of m, times the square root of m. And when I combine those together, my numerator becomes 3 absolute value of m square root of 3m. And the last example, this will become the cubed root of 24 times the cubed root of x to the 7th over the cubed root of y cubed. Again, y cubed is a perfect cube, so that becomes y. And I need to simplify the other ones. So 24 is 3 and 8, which is 2, 2, and 2. So cubed root of 24 equals the cubed root of 2 cubed times 3, which is 2 times the cubed root of 3. And then the cubed root of x to the 7th is the cubed root of x cubed times x cubed times x, which is x times the cubed root of x, or x squared times the cubed root of x. And then combining those together, we get 2x squared cubed root of 3x for the numerator of our fraction. Now, before I end this video, the one thing I do want to mention is as you do more and more examples of these, you are going to pick up shortcuts. But people don't always understand the shortcuts, which is why I just explain everything in the full length so that everyone has a chance of understanding. And that's it for section 8.2.